Welcome friends. In the previous class, we have been learning about the multiple risering, and in this multiple risering, we have seen the concept of what's a end effect and the risering effect, and we have seen the need for adopting multiple risers. If the feeding length is less than the casting length. Now let us continue this. Now we will come across three more terms called feeding distance, feeding length and center line shrinkage. Of course, this feeding distance we have already seen. Now let us learn feeding length and the center line shrinkage. Now there is a difference between feeding distance and feeding length. For example, say this is the casting, this whole thing is the casting and this is the riser, this is the riser. Now around the riser there is a riser zone is there, means in this zone, in this circle there is no shrinkage because the riser is present. Now outside this riser zone you can see here EZL, right, means end effect zone, end zone or simply, so that we can see here this much, say starting from the end. So this is the end of the casting, right, starting from here up to here, this dotted portion is the end zone, means in this portion there is no shrinkage cavity because it is covered by the end effect, and this much is covered by the risering effect. Now here we can see EZL means end zone length. So this is the EZL, you can see this is the end zone length. Next one RZL, that is the length covered by the riser effect. So this is that one RZL, RZL. Next one feeding distance. Feeding distance means it is the sum of riser effect and end effect. Here we can see, so here this much is the what's a riser effect RZL, which is the feeding distance which is covered in the what's a riser zone. This is the riser effect, this is the riser effect. Now from here to here, so from this end to this end, you see this is the end zone, up to this point this is the end effect. So the sum of end effect and riser effect is known as the feeding distance. Now what is the feeding length? Now in this case feeding distance is equal to feeding length, means the length of the casting is equal to, means this portion the length diagonally is equal to feeding distance. That is why feeding length is equal to feeding distance in this section, means casting section is just covered by the riser zones and the end zones. Now we will see the difference between the what's a feeding distance and feeding length more clearly. Now let us see here. Now the length of the casting is a little more than the previous one. Now the length is such that this is the end zone, the end zone length is this much. This much is the riser zone length from here. But if we start from here and measure like this, from here to here, this much portion is the RZL, means start from here and you end here. So this is the riser effect. Now where is the end effect? End effect starts from here, here to here. So that is the end effect. So this sum of end effect and riser effect is the feeding distance. Now you can see there is a gap, right, means that including that gap means a sum of this riser effect, sum of this end effect and sum of that gap, sum of these three components is known as the feeding length, means that is the actual length in the casting measured diagonally in this case, right. So here what we can conclude, feeding length is greater than the feeding distance. Shrinkage porosity forms in the shaded sections of the casting not covered by the riser zone or the end zones. For example, you see up to this much portion the casting it is covered by the riser zone. So, there is no possibility of formation of the shrinkage cavity up to here. Now, this much portion, right, this much portion is the end zone. So, in this there is no chance of formation of the shrinkage cavity because of the end effect. Now, what about to this portion starting from here, say this shaded portion, this is not covered by the riser effect, this is not covered by the end effect. So, there will be shrinkage cavity will be there. Why a shrinkage cavity is there? Because in this case the feeding length is greater than the feeding distance. So, there should not be any gap between EZL and RZL, where EZL is the end zone length and RZL is the riser zone length. But unfortunately, in this case this is the EZL and this is the RZL, there is a gap. So, that is how a shrinkage can take place in this case. Now, let us see some cases. Feeding distance is equal to the feeding length, means the length of the casting is such that the that section to be fed by the riser is equal to the feeding distance. Then what will happen? No shrinkage along the feeding length. Say, so for example, this is the casting and this is the riser. Now, there will be riser effect will be there. The riser effect will be 2T, means the distance covered by the riser to prevent shrinkage, that is 2T. Here we can see. Now, this is end effect. What is that end effect? Distance covered by the edges of the casting to prevent the shrinkage cavity. So, this is 2.5T. So, sum of these components is known as the feeding distance and that is equal to 4.5T. One side it is 4.5T and the other side is also it is 4.5T, where T is the thickness of the slab or thickness of the section of the casting to be fed by the concerned riser. Now, let us see another case where two risers are used, right. In this case also the feeding distance is equal to feeding length. Here we can see from here, right, this is one riser, one side there is 2T, that is the riser effect, and the other side there is 2T, that is the riser effect, and the distance, total distance or the total feeding distance between these two risers is 2T plus 2T, that is 4T, and we have arranged the riser such that the distance between these two risers is exactly equal to 2T. So, there is no question of formation of the shrinkage cavity. Now, let us see another case. Feeding length is greater than the feeding distance. You see here, this is the casting and there is single riser is there, this is the riser. Now, this is the length of that section to be fed by this casting, this riser. Now, here we can see riser effect is there, means distance covered by the riser to prevent the shrinkage cavity, that is 2T, and this is the end effect 2.5T, that is the distance covered by the edge of the casting to prevent the shrinkage cavity. So, this is 2.5T. So, in this portion there is no shrinkage cavity because of the end effect. In this portion there is no shrinkage cavity because of the riser effect. Now, what about this portion? This portion is not covered by the riser, or it is not covered by the riser effect and it is not covered by the end effect. Then what will happen? There will be shrinkage will be there. You can see this is known as the center line shrinkage, right. So, center line shrinkage can take place when feeding length is greater than the feeding distance. Feeding length means the actual length falling under the load of the riser. So, this whole length is the feeding length, whereas feeding distance is the sum of the end effect and the riser effect. So, in this case the feeding length is greater than the feeding distance. So, that is how a center line shrinkage cavity defect is arising here. And we can see another case where there are two risers and for this one riser, one side there is 2T, that is the riser effect. So, there is no question of shrinkage cavity in this region, and this is another razor, and here there is razor effect 2T, where T is the thickness of the section. Now, in this region also there is no shrinkage cavity because of the razor effect. Now, what about this portion? This is not covered by this razor, the left side razor. This is not covered by the right side razor. Then what will happen? Of course, there is no question of the end effect because there is no edge. Only two razors are there on both sides. Then what will happen? The center portion, which is not covered by either of the razors, there will be shrinkage cavity. Here also feeding length is greater than the feeding distance. Now, here what is the feeding distance? The feeding distance is, here it is 2T and here it is 2T. The total feeding distance between these two razors is 4T, whereas the feeding length, the actual distance falling under the two razors is greater than the feeding distance. That is how a shrinkage cavity will take place. So, we will call it as the center line shrinkage here also. So, this is the center line shrinkage. Ways to increase the feeding distance. So, now just now we have seen that when the feeding length is greater than the feeding distance, a center line shrinkage defect will arise. Now, at any cost we have to see that the feeding distance we have to increase or to improve. How to improve? We can place a chill here. For example, this is the casting and this is the razor, and again here you can see there is 2T, that is the razor effect, and right here there will be 2.5T, that is the end effect, and we can increase the end effect by placing a chill here. So, chill is a steel block which is placed on the side of the mold wall, right. Then what will happen? It rapidly increases the heat. Because of that, more part of the casting will be solidifying in lesser time. That is how the end effect will be more compared to the case where there is no chill. So, by placing a chill on the inside the mold, we can increase the feeding distance. Thus, we can also increase the efficiency of the razor. Next one, let us see. We are learning about the modification of the design. So, instead of going for a single razor, if we go for multiple razors, we can have a better efficiency. That is what we have seen under the multiple razoring. Now, we will see another topic called bottle razoring. By incorporating bottle razoring, we can improve the razor efficiency. What is this bottle razoring, or what is a bottle razor? Bottle razoring. A primary shrinkage hole, right? A pipe is created quickly in a razor, right? So, this pipe, because of this pipe, the metal will be forced inside the mold cavity. A pipe is created on the sides of the razor. Because of that, the molten metal which is present in the razor will be pushed inside because of the atmospheric pressure, right. If the liquid metal in the razor is not open to the atmosphere, then the razor will not function. So, because of the atmospheric pressure, once a pipe is created on both the sides around the surface, right, the molten metal will be pushed inside the cavity. Atmospheric pressure is necessary to push the metal into the casting. A bottle razor, it is also known as Hein razor, has such a small area at the top diameter that will begin to pipe very quickly. What is the specialty of a bottle razor? Its top diameter will be very small, right. So, because of that, the piping takes place very quickly, means a pipe will be created at the top, means the molten metal near the mold wall will be solidifying quickly. A circular pipe is created and inside there will be liquid metal that will be pushed into the molten cavity. So, in order to have sufficient feed metal volume, these razors must be taller than the classical design. So, usually we have seen that especially in the NRL method, what is the H by D ratio? It will be between 0.5 to 1. The H by D ratio should not be greater than 1. But here the length of the razors will be more than the conventional razors. The height to diameter ratio is 1.5 to 1. So, this is the typical height to diameter ratio for a bottle raiser. Now, this is the typical appearance of a bottle raiser. You can see this whole thing is a bottle raiser. See, it is slanting, right? At the bottom, this is the bottom diameter. You can see raiser bottom diameter is this much starting from here to here, whereas this is the top diameter. You see, top diameter is very small, whereas bottom diameter is very large. And here we can see this is the gate, right? Through this gate, right, molten metal enters, and this is this side is the casting, and this is the height of the raiser. You can see this is the height of the raiser. Now, we come across another interesting term called significant modulus of the casting. What is this significant modulus? This significant modulus, we can see, say there is a difference in the diameters of the raiser. At the top it is very small, at the bottom it is very large. Now, there is a difference between the diameters both at the top and the bottom. Now, half of this difference in the diameters is known as the significant modulus, right? Half of that difference, that is indicated by ms. Now, at the bottom it will be 2 ms and this side there will be 2 ms. Formula for bottle raiser. How to design the bottle raiser, right? Raiser bottom diameter is equal to 4 into ms plus raiser top diameter. The casting feed metal required is equal to 4% of the casting weight. Raiser feed volume determined by the raiser top diameter and height to diameter ratio. Use tallest raiser possible for the flask size, and raiser height is equal to h/d ratio into raiser top diameter. Now, this is the feed metal table for bottle raiser in different cases, means when the h/d ratio is changing in different cases. So, these are the feed metal diameters in different cases. Here we can see h/d ratio is equal to 8:1. Now, when the top diameter is 10 mm, the feed weight is equal to 44 grams. When the top diameter 20 mm, the feed weight is equal to 352 grams. When the top diameter is 30 mm, it is 1186 grams. When the top diameter is 40 mm, the feed weight is 2813 grams, and when the top diameter is 50 mm, the feed weight is 5495 grams. So, these are the cases when h/d ratio is equal to 8:1. Now, h/d ratio is 6:1. If that be the case, when the top diameter is 10 mm, the feed weight is 32 grams. When the top diameter is 20 mm, the feed weight is 264 grams. When the top diameter is 30 mm, the feed weight is 890 grams. When the top diameter is 40 mm, the feed weight is 2110 grams. When the top diameter is 50 mm, the feed weight is 4121 grams. So, these are the cases when h/d ratio is equal to 6:1. Now, let us see another case where h/d ratio is equal to 5:1. When the top diameter is 10 mm, the feed weight is 28 grams. When the top diameter is 20 mm, the feed weight is 219 grams. When the top diameter is 30 mm, the feed weight is 741 grams. When the top diameter is 40 mm, the feed weight is 1758 grams. When the top diameter is 50 mm, the feed weight is 3434 grams. So, this is the case when the h/d ratio is equal to 5:1. Now, let us solve a problem. The weight of a casting is 85 kilograms. The height of the cope is 330 mm. If the significant modulus of the casting ms is 15 mm, design the bottle raiser for the casting. Now, we have to design the bottle raiser. Casting weight is equal to 85 grams given, cope height is equal to 330 mm, significant modulus of the casting ms is equal to 15 mm, feed metal required, formula we have already seen, 4% of the casting weight, that is equal to 3400 grams. So, this is the feed metal. Now, we need to, for this feed metal, we need to find out the dimensions of the bottle riser. Choose from the table the riser top diameter and H by D ratio corresponding to 3434 grams of the feed metal, right. So, this is the what say standard table for the bottle riser, and here we can see that much what say feed metal we can see here in this case 3434 grams. So, means so this is the diameter, top diameter of the bottle riser, and say this is the H by D ratio 5:1. Accordingly, we can design the bottle riser. That be the case, then what will happen? Riser top diameter corresponding to 3434 grams of feed metal is equal to 50 mm. H by D ratio is equal to 5:1. Now, riser bottom diameter is equal to 4 into ms plus riser top diameter, where ms is the significant modulus. Now, that is equal to 4 into 15 mm plus 50, that is equal to 110 mm. So, the riser height is equal to H by D ratio is 5:1. So, riser height is equal to 5 into 50, that is equal to 250 mm. So, this is the riser height. And what about the bottom diameter? Bottom diameter is 110 mm. What about the top diameter? 50 mm. So, this is the design for the bottle riser in this case. Now, we are seeing learning about the case how to modify the design of the riser to improve the riser's efficiency. Under that, we have seen we can go for the multiple risers and also we can go for the bottle riser. Now, there is a term called, another topic called safety margin. By what say incorporating the safety margin, by what say carefully designing the safety margin, we can improve the riser's efficiency. Now, let us see what is this safety margin. You can see this one, this is the casting and this is the riser. Now, once we what say pour the molten metal, immediately this much portion, right, a pipe is created here on the sides. Now, inside the liquid metal and it flows this liquid metal here and it will be feeding the casting. Thus, there is a what say cavity will be created here, a cavity will be created. So, this much portion there is a cavity and this is the solidified portion. Now, this cavity is like a right pipe and it comes and it is stopping here. Now, what is this? This is the safety margin. Safety margin SM is defined as the distance from the riser casting contact surface to the tip of the riser pipe. So, this is the safety margin. Now, what does this indicate? Now, when if this safety margin is just touching the what say casting, no problem. Suppose if this safety margin is going below the casting surface, means what does it mean? There is shrinkage cavity is there. On the other hand, if the safety margin is too much, what does it mean? Means from this riser you see only this much length of the riser is utilized for the feeding of the casting. What about this much length of the casting, starting from the surface of the casting to here? That much portion of the riser is not involved in the feeding of the casting. Now, if the safety margin is more and more, what will happen? That extra portion or that extra length of the riser is not involved in feeding of the casting, means that is a wastage only. So, the safety margin should be minimum, it should not be too much. On the other hand, it should not be 0, right? 0 means it will be just touching and it should not be negative. Safety margin for different alloys is to be found out by experimentation. The height of the riser should be such that the safety margin does not exceed 2 to 5 centimeters, right. If the safety margin is more than 5 centimeters, certainly there will not be any shrinkage cavity, but that is a wastage of the riser material. Whatever what say length of the riser covered in that safety margin is waste, and on the other hand it should not be too less, right. In such a case there may be a shrinkage cavity and it should not be negative. So, the height of the what say the length of the safety margin should be between 2 to 5 centimeters. So, this safety margin, by properly designing the safety margin, by conducting the experiments, and we have to find out the safety margin for different cast alloys. Accordingly, we have to fix up the height of the razor, then the efficiency of the razor will be improved. If the safety margin is negative, then the razor pipe extends into the casting. In such a case, shrinkage cavity will arise in the casting. Next one, there is another topic called razor necking. So, this is also a modification to the razor design. With this also, with this razor necking also, we can improve the efficiency of the razor. What is this razor necking? Now, you can see here. So, this is the razor and the casting is this side. Now, the razor is given a necking here. So, this will improve the efficiency of the razor. Now, here we can see T is the thickness of the casting of the section to be fed by the razor, and D is the diameter of the razor. HN is the thickness of the neck. This much portion is the HN, is the thickness of the neck, that is equal to 0.6 to 0.8 times the thickness of the casting or the thickness of the section to be fed. Next one, Ln is the radius of the neck. This is the Ln, that is equal to D by 3, where D is the diameter of the razor. Next one, Wn is equal to width of the neck, that is equal to 2.5 times Ln plus 0.18 D. So, by incorporating razor necking, we can improve the efficiency of the razor. Finally, tapering is there. By tapering means by giving a taper to the casting, we can improve the razor's efficiency. Here we can see this is the casting, this is the casting, this is the casting, and this is the razor. Now, taper is provided, you can see here, here the thickness is more and slowly the thickness is reduced. This will definitely improve the performance of the razor. Now, here we can see this is the end zone length, end effect, and here we can see this is the razor zone length, right, and here a taper is given. So, because of this taper, the efficiency of the razor will be certainly improving. Now, how to choose this taper, and this is the graph available to us, and here we can see on the x axis width to thickness ratio W by T on the x axis. On the y axis we can see taper, that is equal to height by length, height of the taper divided by length of the taper, and here we can see the width to thickness ratio 1 to 3 up to 9, and here we can see the taper h divided by L. So, it is this much, right. So, by considering this graph, we can successfully design the taper for the casting, which will definitely improve the efficiency of the razor. Now, computers in design, in razor design. So far we have been learning about the different methods of the razor design. We have seen the Keynes method, which was very tedious and time consuming. Next we have seen the modulus method. The modulus method, it requires that we need to find out the surface area of the casting. Of course, in these lectures we have considered some simple shaped castings. So, that is how we were able to find out the surface area of the castings very easily, but in practice the surface area would be very complex. In such a case, calculating the surface area would be very tough. That is how even the modulus method has got certain practical difficulties. And finally, we have seen the NRL method, the Naval Research Laboratory method, where the time required would be very less. Within no time we can design the razor, right. Also, this surface area does not come into picture, but still we need to check the our design using the feed volume concept, whether what we have designed is proper or not. That way, that also takes time, but fortunately the computers have come into picture in the razor design. Using the computer softwares, we can also design the razors. So, we will see certain important sorts what say computer softwares that have been developed around the world to for the razor design. Important softwares for the razor design. One is the MagmaSoft, another one is the AutoCast, another one is the SolidCast, another one is the ProCast, and another one is the Cast CAE, and there are more softwares which are available for the razor design. Let us quickly review what these softwares are. MagmaSoft, right? It was developed by Magma, Germany. MagmaSoft predicts the following characteristics, right? It predicts the razoring and gating system. We can design razoring and gating system. Internal porosity is predicted by this software MagmaSoft. Residual stresses are predicted by this software. Hot tearing, that is a defect which is a cracking of the casting during solidification. So, this hot tearing is also predicted by MagmaSoft. Finally, the microstructure, which is very important as far as the properties are concerned, that is also predicted by MagmaSoft. But though it has got several components, one component is the design of the razoring and gating. So, we can using this MagmaSoft we can design the razoring and gating, and this is an example using the MagmaSoft method, right. So, this is the computational model of the original rigging as used in the MagmaSoft simulation. You can see, yes, these are all the sleeves where sleeves are used, and here we are placing the chills, and this is the pouring cup and this is the sprue, and it will successfully predict the design of the razor in different cases, when sleeves are used, when sleeves are not used, when chills are there, when chills are not there. Likewise, in different cases what should be the dimension or the design of the razor, it will be successfully predicting. Next one, there is another software called AutoCast. So, this was developed by 3D Foundry Tech Private Limited, Mumbai in India, right. It has got three modules. One is part module, second one is the mold module, next one feed module and gate module, and so on. Now, the feed module helps the foundry man to optimally design the razor and to optimally locate it in the right position, right. So, this software we can use, and this feed module will help us to design the razor, not only to design the razor, to locate the razor in the right position. So, this software can be used. So, this is an important software produced in India, and this is the optimization of the razor size and evaluation of the insulating sleeve by AutoCast feed module. Here we can see, right. So, here the size of the razor is optimized and where an insulating sleeve is used. Next one, next software SolidCast. It contains the razor design wizard and gating design wizard. It can be used to simulate castings poured in grey cast iron, ductile cast iron, steel, aluminum, copper based alloys, nickel based alloys, and almost any other alloy. And here we can see the simulation using this software under razor shrinkage predicted in grey iron casting simulated with SolidCast. Next one, we have the ProCast software. It was developed by ESI group. It has different modules like quick cast, right, SAL, SA3D, etc. right. Among these modules, SAL, SA3D helps to calculate the razor size, gating and running systems, especially for high pressure die casting process. Here we can see simulation using ProCast. Next one, Cast CAE. So, this is another software developed by a Finland company. This tool has different modules: cast design, cast check, and so on. Among these modules, cast design is a simulation package that helps in designing the razoring system for the casting. And here we can see simulation using Cast CAE. Friends, till now what we have learned? We have seen in these two lectures, we have seen the feed volume concept, right. So, alpha into Vc plus Vr is equal to eta f into Vr, where Vc is the volume of the casting and Vr is the volume of the riser, and alpha is the percentage volumetric shrinkage of the cast metal, and this is different for different cast alloys, and eta f is the riser efficiency. What is riser efficiency? It is the ratio of feed metal available to the total volume of the riser. We have also seen the methods to improve the riser efficiency. The riser efficiency can be improved by achieving directional solidification. Again, directional solidification can be achieved using insulating sleeves. Directional solidification can be achieved using chills. Directional solidification can also be achieved using exothermic materials. Next one, the riser efficiency can be improved by adopting blind risers. So, this is what we have learned. Finally, we have learned that modification of the risers design also helps us to improve the efficiency of the riser. How to modify the riser design? One is the multiple risering, right? Multiple risering. Second one, bottle risering, safety margin, and we have seen the other factors which will be helping us to improve the modify the design. And this is the fifth lecture I am delivering on the design of the risering system. In this 5 lectures, what we have learned? We have seen the Keynes method, and in the Keynes method we have to find out the freezing ratio, and also we have to find out the we have to find out the freezing ratio, and accordingly we have to find out the design of the riser, and we have seen that Keynes method is tedious and time consuming, and we have seen the modulus method where the freezing ratio does not come into picture, but we have to calculate the modulus of the casting and the modulus of the riser, where modulus is the volume to surface area, ratio of the volume to surface area, and surface area we need to calculate. And finally, we have seen the Naval Research Laboratory method. So, this was developed by the US Navy, and here the modulus does not come into picture, the surface area of the casting does not come into picture, only shape factor comes into picture, and using the shape factor we can directly find out the design of the riser using the riser curve and also the riser height selection charts. That is what we have learned in these 5 lectures. Finally, we have seen how to improve the riser's efficiency. So, with this we are closing the design of the risering system, and in the next class I will be delivering the lecture on the design of the gating system. Thank you.